Broadcast is now starting. All attendees are in listen-only mode.
Hi everybody, thanks for joining us for our webinar today. We will get going in 1 minute. All right, I'll get going now. So greetings to everyone who's joined us. Today we're going to be speaking about 5G phased array antenna simulation essentials. Our presenter will be Mohammed Sameh. This is Chris Cowan here, and I'm going to give a quick introduction to my company, Ozen Engineering, about our capabilities, ANSYS consulting, training, software, etc. Okay, Ozen Engineering is a company that's focused on simulation. We use finite element analysis and computational fluid dynamics to solve multidisciplinary engineering problems. I'm happy to say that in the most recent year, we were chosen as the ANSYS Channel Partner of the Year for North and South America, and we are certified as an ANSYS Elite Channel Partner. As a channel partner, we sell ANSYS software. We hold training classes at our facility, online and at remote facilities. We provide technical support to our customers, and we also provide engineering consulting services. So if you have a project that you're having trouble setting up, or you want to kickstart a project, or you don't have software in the first place, please contact us about engineering consulting services. We work with the full suite of ANSYS products, including fluids, structures, electronics, optics, and multi-physics combinations of those. We also offer cloud services, a couple different options, Ozen Cloud and ANSYS Cloud. If you're interested in trialing either of those, please contact us. We generally do a webinar every Wednesday or every other Wednesday at 11 a.m. Pacific time. We see here on the left side our upcoming topics, including today's and through the remainder later this year at least. In gray are the topics that we have done in the recent past. All of these topics available, including those on the right. You can download the content, the recording of the webinar from our website at ozeninc.com/webinar library. You can subscribe for any of the upcoming webinars. We'll be happy to have you join. And if you'd like to receive a monthly newsletter from Ozen Engineering, you can subscribe on our website. One thing I'd like to say is that ANSYS has been putting a lot of effort recently into building up cloud solve capability. This is really the future, the way that people will be using the software ongoing in the future. So why work with cloud? Most importantly, one-click burst to cloud capability. So you can have mediocre hardware on site, and you can still solve large, complicated problems using the cloud. You get to choose. ANSYS offers different varieties of hardware that you can use based on number of cores and quantity of RAM available. So you can choose which one is most appropriate based on how large your problem is and how quickly you need it solved. ANSYS Cloud offers web-based 3D post-processing. Why do we like that? Because you can upload your file to the cloud, you can solve it. Most likely you're going to generate a large results file, and you don't need to download that large results file to your machine. You can do all your post-processing online. This solution is intended for ANSYS. It's made by ANSYS. It's a single solution. It's streamlined and it works, so you don't have problems operating or configuring this. And by the way, if anyone is interested in a free trial of cloud, please contact Ozen Engineering and we'll be happy to set you up with that. So you can reach us by email, info@ozeninc.com. You can call us directly, or you can submit a form through our website. On top of that, I'll say that we are always looking for mechanical and electrical engineers. So if you're interested, please send in a resume. On to our presenter, Mohammed Sameh. He's been working in the antenna and RF development field for 20 years in the wireless industry. He serves as a technical consultant for topics related to 5G, Internet of Things, system simulation, and testing and certification. Over those 20 years, he's been working with ANSYS electromagnetics tools with a lot of time put in on HFSS for antenna design. And he has a number of patents and publications, a member of the IEEE and AMTA, and Sameh has earned his PhD in electrical and computer engineering from Ohio State University. So without further ado, I'll turn this over to Sameh so he can continue with the presentation. Thanks for your attention, everybody.
Thank you, Chris, and hello, everyone. We're happy to present for you today some capabilities ANSYS tools have to help phased array antennas for 5G applications. Let me try to share the screen here.
So I don't see your screen yet, Sameh.
Yeah, I'm.
Okay.
So do you see it now, Chris?
I see it in presenter mode.
Change the screen.
Okay.
Perfect.
Thank you. So our agenda today, I summarize it into 3 bullets here. We'll just take a snapshot on 5G promises and needs. We try to categorize phased array antennas, and then we're going to dive deep in our simulation essentials of the phased arrays using ANSYS tools. So 5G promises capacity boost of up to 10 gigabit per second, super high speed, high resolution of download of high definition 8K videos, virtual reality, augmented reality, and others. A massive number of connected devices, of IoT devices, including sensors, all kind of gadgets, tracking devices, trillions of them are expected to be out there. The last and one of the important promises is the low latencies. Low latency, fraction of millisecond to get the information communicated from one point to another. And this is very important for mission critical, such as like autonomous driving, smart cities, remote surgeries, and others. So to make these promises happen, to fulfill these promises, already the 3GPP standard body have been working on expanding the frequency spectrum, and they categorized or they divided into 2 frequency range, FR1, which is sub 6 gigahertz, with carrier aggregation, collecting all possible small bands or wide bands together to serve specific needs, a lot of flexibility. And the second band is the millimeter wave, which provides wide bandwidth that can make the high speed and high resolution happen. So we'll try to focus here in our phased array antenna, which I would say it's a space filtration and selectivity. So now the what we have on the base stations, and most of the antennas are kind of like fixed beam, wide beam. So these things are going to change. Try to utilize the space more smartly and select certain angles to be targeted by the antenna beam, and others be avoided. And this can be rephrased in terms of the communication link optimization to make the link stronger by having high gain antenna in certain direction, and interference mitigation by steering a null to a certain source of interference undesired, and selectivity between users. So currently users are being separated in frequency or time or code, which are the standard frequency division multiple access or time domain multiple access or code CDMA, and the space is going to be part of that selectivity as well. To make this happen, the enabler for this is phased array antennas. It's a must. So the phased array antennas is going to provide a real-time reconfigurable beam, replacing fixed beam antennas that exist in the current technologies. So phased arrays, not all phased arrays provide electronic scanning, but what we're talking about today is the electronic scanning phased arrays, so where the beam can be steered. Some other phased arrays and other applications, they have fixed beams. They can have spot beams that are fixed, that are not moving around, no dynamic, no time variation. So again, these electronic scanning phased arrays are going to have a real-time beamforming to direct the power peaks to certain angles to ensure the communication link and avoid interference by steering the nulls. And we have had many applications in both. One of them, like GPS anti-jam for specific government applications, where the GPU receiver can be an array, and if there is a jammer coming from a certain direction, you create a null from this angle, or from that to block the jammer at that direction. So how are we going to achieve this? So the phased array provides continuous aperture distribution control, amplitude and phase, and this has a price, which is the complexity of the design, of the manufacturing and testing and operation. When we talk about aperture, dish antenna is an aperture, but it doesn't provide this control of the fine control of each square inch of the aperture like the phased array does. So phase arrays can be divided into radiating elements and beamforming network, as simple as this. And the architecture, there are different ways to decide, but if we stick to these two, the aperture, the size of the aperture, the area of the aperture, the shape of the rim of the aperture, the lattice where you populate the elements, the spacing between elements, and so on. The beamforming network, it's a corporate Rotman lens or serial fed, and we are not going to focus on the beamforming network in our presentation today. Our focus is going to be more on the aperture side. Simulation-wise, we have two categories: infinite array and finite array. And we're going to see what the difference and which one is realistic and which one is easier. So, so our simulation is going to start with the idea of having a periodic structure. And this periodic structure can go to infinity in all directions. We're talking about planar structures. We're not talking about conformal arrays here. So our simulation will provide three options that we are going to keep repeating these options along the presentation. An infinite array where we build a unit cell and create walls to populate this cell in XYZ plane. And then we have the finite array simulation. We have two ways to do that. One of them, we call it finite array domain decomposition method, that takes care of the edge effect, where the infinite array doesn't take care of that. So the truncation of the size of the array is taken care of in this finite array model, which can be done also explicitly without the domain decomposition. And in the explicit mode, you basically build each element on its own, so it doesn't have to be a uniform periodicity, and even it doesn't have to be planar. You can go non-planar array at this point. The explicit is the most flexible, the most accurate, but it's the most expensive computational wise. We're going to compare these three in the next slide. So the decisive factors which want to go after, or the considerations, are the edge effect, the truncation. If you don't care about edge effect, you can go for the infinite array. In most cases, the practical cases, we have an edge, so truncation is important for many people. So we have to go for finite array. And of course, if you don't have a periodicity, or you have non-planar structure, so you have no choice but going to the explicit, the most expensive, computationally expensive simulation tool. Okay, we're going to introduce Floquet ports and master-slave boundaries that we use in the simulation. So here, since we are trying to compare these three options, this slide is going to kind of like summarize. So we have one option is infinite array and two options under the finite array. So infinite array is basically, again, creating a single cell and then using master-slave, or I call it mirror walls, to populate this element in XYZ from minus infinity to infinity. It's the most efficient. It's the least demanding from the hardware in terms of memory, but it ignores a lot of things like edge effect, like we don't also have ability to do some post processing to change, to taper, or to do a magnitude difference between one element to another. And also it might not be practical in some situation. In the finite array, so we have the explicit where each element is basically placed in the place in the location you want to. It doesn't have to be uniform. Periodicity, it doesn't have to have any periodicity at all. But this comes on the expense of computational cost. More on the flexibility, you can provide non-uniform amplitude or magnitude, phase, whatever you want. Again, we can do non-planar conformal array in this case. The finite array domain decomposition method is basically an efficient way to solve the finite array. And we're going to see how we do this. And it provides some flexibility. It allows magnitude taper. Of course, it gives edge effects, the truncation into the analysis and the results. And also the mutual coupling from the center elements to the edge elements are calculated correctly. And it's more efficient than, much more efficient than the explicit. But it has limitation, which is being planar and being purely periodic. It has to be uniform. So it's not like the explicit, you can do whatever you want. Okay. So here, one important geometry aspect of the array is the lattice. So we're going to talk about uniform lattice today, which there are two popular ones, rectangular and triangular. We'll see some pictures. And basically for the rectangular lattice, we're going to create in the infinite, we use some mirrors in XY axis. And for the triangular lattice, we have several options. We can use hexagonal wall mirrors, or rectangular wall mirrors, or triangular. The easiest one, or the most obvious one, are the hexagonal ones, and we're going to focus on this in our presentation today. So this chart here present the trade-off between speed and accuracy between the three methods, where the unit cell infinite array method on the top in terms of speed, it's the fastest way and it's the simpler way, simpler setup, and the most computationally efficient in terms of resources, memory, and time. On the other end, the explicit simulation on the bottom here that provides most accurate results, including edge effects, mutual coupling, and also provides the most flexible architecture. It doesn't have to be periodic or uniform, and also we can provide feeding with different amplitudes and phase, and in between comes the finite array domain decomposition method, which kind of like in between in terms of presenting the truncation effect and edge effect, and saving the resources and computational requirements that explicit simulation needs. So let's jump in. So I'll jump here on for the infinite array, we use these mirrors. We call it master-slave boundaries. And these master-slave boundaries are basically the walls that create the periodicity in two directions, x, y. And also one of them, the slave in HFSS setup, you can set up the scan angle, and that's where actually where the beam scan angle is set up. So here in this picture in front of us, we put 30 degrees, and the red arrow points to the 30-degree, and this will generate the phase delay requirement between these two planes and the phase shift requirement on the feeding of the elements to achieve the scan angle. In the triangular lattice, here in front of us, we have the hexagonal cell, which has 6 walls instead of the 4 walls of the rectangular cell previously shown. And now we have to have 3 pairs of master-slaves boundaries, like shown here in the picture. And the boundaries will have 6 elements. The list will have 3 masters and 3 slaves. And are defined together. The master 1 and slave 1, they go together, and 2 and 3, they go together, and 3 and 3, they go together. In the left picture here, you can see the hexagonal cell surrounding a circular element. So the element doesn't have to be circular, but the 3 elements, adjacent elements, create a triangle. And that's what the name comes from, the triangular lattice. And the black arrows, those are the kind of the lattice formation vectors. And these 2 vectors basically point from one point, from like start at one point on an element and ends on the same point on the adjacent element. And it's here we have the horizontal one and we have the 60-degree one, and those are enough. These 2 vectors are sufficient to describe the whole array. So, of course, in the crystal, in the solid state physics, when we go 3 dimensions, these 2 vectors become 3, and crystal structure usually are described by similar vectors like that. In the rectangular, it's easy because there is no 60 degrees, it's just 90 degrees, 2 vectors. Okay, so now we're talking about like the unit cell that we are building infinite array for. So the master-slave boundaries are need to be set up correctly for triangular lattice or rectangular lattice, and we use two pairs or 3 pairs based on them. And then the second thing is the Floquet ports. So the Floquet ports are basically, we use these two vectors, the lattice vectors, AP, and we show that they are 60 degrees in the triangular and 90 degrees in the rectangular lattice, as we see here on that picture. So these Floquet ports, so if we have a structure like what we have to the right here, it's like as if it's an open waveguide structure. So you can imagine that we have a port from the bottom bumping RF energy on the rectangular tube, and ending at a certain point, radiating this energy, and we capture this energy with the blue square, and then we create this Floquet ports. And these Floquet ports, basically, it's very essential for periodic structure analysis, not only in phased arrays, but frequency selective surface and other applications. So they do several functions. Important thing is they just generate the Floquet modes. They absorb the modes generated by the port, which is at the bottom here. And it's they basically work kind of like for their modes, the exciting mode and terminating modes or terminating waves. They decompose the fields into Floquet modes, like similar to TE and TM waveguide modes in the similar concept. And also they work as to absorb the modes defined by the port, so as if part of it, as if they are kind of like absorbing boundary conditions for the excitation coming from the defined port in the bottom. Okay, so so I want to go back. So this is the essential part of building infinite array. Now we're going to switch to the finite array. And before we do this, I want to do some kind of like comparison between, in previous examples, between the speed and accuracy of the two finite array methods we described, the domain decomposition method and the explicit method. And here's an example of 64 elements of linear polarized elements. And you can see here in the comparison in terms of computational time and memory, it took 2.75 hours for the DDM method versus 6 hours in the explicit array simulation, and the memory 10.5 gigabyte versus 28 gigabyte for the explicit. So there is like a 2.2 factor of speed faster, and more than that, it's like 2.7 factor in the memory. So it's a lot of saving, especially for larger structure. So what is the take is accuracy. So let's figure out how bad this DDM in terms of accuracy. So we have here two examples. We have two plots on top of each other, a pattern plot. So the dashed red is the DDM. I'm talking about to the left, and the blue is the explicit. And basically in the main loop and the up maybe to like 90 degrees, almost the same. They are on top of each other. the deviations start to appear maybe in the back lobes, and it's not by much. It's maybe at the peak of the back lobe, it's about maybe 3 dB or 2 to 3 dB difference. It's at lower level. So I think this take in the accuracy is very negligible in most applications compared to the save in the speed and computational resources. Another comparison here to the right, which is one element instead of the array, just one element, embedded element pattern, and you cannot tell the difference. There is a small, very, very small difference, but it's very negligible. Okay. So the take is that this DDM method is really something that is useful, saving computational resources, time, and the sacrifice in the accuracy is negligible. Of course, there's another thing that we talked about, which was the flexibility. The explicit has the most flexible, so you don't have to have a uniform array. You don't have to have a planar array. You can do amplitude and phase whatever you want. So DDM has certain limitations in that aspect. So okay, now we saw how we build infinite array using a unit cell. We're going to talk about how to build a finite array for DDM. Of course, building a finite array for explicit is nothing new. It's just basically as if you're building a model from the scratch for any antenna, but this antenna has certain elements or subsystems that are being repeated the way you want. Maybe it's repeated with some doesn't have to be uniform, it doesn't have to be planar, as we said. So you build it one by one. So we're not going to talk about building the explicit, but the DDM requires some procedure to build the array. So the finite array for DDM, it starts with the unit cell of an infinite array. So you create a mesh of an infinite cell, a unit cell of an infinite array, and you take this mesh, use it for the DDM. And that's where the computational efficiency comes from. The explicit array mesh the whole structure, but the DDM just relies on meshing one unit cell and then take this mesh and repeat it for other cells, which are finite in number. So, and you import the mesh from the unit cell and disable any meshing refinement the model will try to do to enforce using the same mesh for each element in the finite array. And by this, you save a lot of time, and you know from the beginning that for each cell, it's already, the mesh is sufficient for conversions, for accurate results. So you have to take care of that when you build your DDM finite array. There is some in HFSS some creation. We're going to go through this, the secret finite array, how to repeat, how to make number of elements you want. Fluke ports that were used in the infinite array are going to be substituted by or replaced by radiation or perfect match layer boundaries. we're going to keep the master-slave boundaries on the unit cell, but they will have less function than the infinite array. So now the phase shift, the scanning angle that we saw that are being set in the slave boundary that follow the master is not going to be the same anymore. So we don't care about setting the phase shift for the scan angle here in this method. In the slave boundary, there's another way we're going to see it. You set the high power computing, and at the same time you check the license, because this DDM method is only available if you have HPC license, and then you run the model. So let's dive into some details for these steps. Okay, so here is how you create a finite array using HFSS. There is under HFSS model, create an array. You get a window like this. We know that we have two vectors defining our lattice, vector A and vector B, and these vectors here, you can define them using master-slave pair. So if you see on that window, vector A is defined by master A1, and the size of elements is 21. Vector B is defined by the pair master 2, and we have number of elements 21. Okay, so we go to the right. So if you click the second tab, which is active cells, you see such a picture of 21 by 21 elements. In this case, it was, well, actually you cannot tell if it's a rectangular lattice or triangular lattice from this, because you always see this rectangular lattice, but we'll see how to project it on the triangular lattice in next slide or the slide after. What we need to mention here, there are three types of elements. Active elements, which you're going to feed the RF energy into, that the elements that have the beamforming network in the back, the actual antenna elements that are pumping power, radiating power, and they are represented by the blue little squares. And then we have a dummy elements or passive elements, which are presented by the white little squares. And basically those are elements physically exist. So they are part of your structure, your mechanical structure. You build them, you put them in the array, but they are not connected to the beamforming network. They are connected to matched load. So they are terminated elements. So that's the reason we call them dummy or passive, but they are there. And then the bedding. The gray ones at the corners are the bedding or air elements, and those elements don't exist physically, mechanically. You don't build them. They are not there. They are not part of your structure. And this basically, this bedding is what you kind of like use to create the rim form of your the rim shape of your aperture, like what we mentioned earlier. So bedding, there is no physical presence of any elements, no mechanical presence, it's just air. And the dummy elements are elements exist but terminated by 50 ohms or matched loads, and the active elements are the elements that are connected to the beamforming network. So this is very important. So now let's go see if it's a square, it's going to be easy because it's going to project one-to-one. The trick is when it is a triangular lattice. It's a little bit tricky. So the triangular lattice, if you remember here, the vector A and vector B are defined by the master 1 and master 2. So the master slave pairs defines the vectors, vector A and vector B. And that's what we see here. So here, if I want to create a 19 element triangular lattice structure to the right, I start with 5 by 5 elements or grid instead of 21 by 21 like last time. So it's 5 by 5 here. And those are 25 elements. So, and then I bed 6 elements, the corner elements here. So basically I bed the ones, like those 3 ones here at the bottom corner. I bed the other 3 on the right top corner, and I end up having the 19 element. So 25 minus 6 is 19. So this one is a little bit tricky. Sometimes you need to go back and forth to make sure that you get what you plan to get by bedding the right elements. Okay. Okay, so building finite elements. So we said we're going to take the unit cell mesh, we do the import mesh, and we kind of like disable any mesh refinement. We don't need any mesh refinement. We just take this whole unit cell and repeat it 19 times or 7 times or whatever number of elements through this active passive bedding, the create an array option. And then we go for the results. So what are the typical KPI, key performance indicators? We look at the return loss, the coupling between elements, isolation, the patterns carry some other information, gain, beam width, side lobe level, sometimes null location. We have also some scanning angle that create losses in the gain, higher losses than others. Of course, with the planar structure, there is this cosine theta loss for the projected area, but more than that happens with the coupling and surface waves and other mechanisms that can cause scan blindness at certain angles, and these angles, of course, shouldn't be part of your design. You have to be careful about that. So I go back here. I mentioned return loss and coupling. Typically, we don't expect the S11 or S21 or to be dependent on the scan angle, but in our case, it is. They are dependent on the scan angle theta and phi. So S11 is a function of theta and phi, and Sij, coupling between any two elements, or isolation between any two elements, is dependent on the scan angle. And here are just sample of popular or typical powerful HFSS plotting tools. You can get rectangular, Smith, polar, three-dimensional patterns, color graded, and so on. So these are typical things you can use, but with understanding that this is scan angle dependent. Okay, so one thing that we mentioned in the master slave, there's an option of having the phase delay that is basically for infinite array, allows you to steer the beam. But we said we're not going to do this, don't care about it in the finite array. So what should we do in the finite array using DDM? So there is some post-processing option that there is called edit sources. So basically you can go for every element port and you define the amplitude and phase. You can do this by yourself if you know exactly what you what scan angle translate into what phase shifts of elements, or HFSS gives you what's called finite array beam angle calculator. It's an option that you just say, I want this specific scan angle, theta equal 30, phi equal 45, and it automatically projects the required element phase shifts, and also with one click it can update the phase shifts in the ports, or edit sources post-processing that I mentioned that you can change manually. So this is one part or one step in the procedures for DDM that we mentioned earlier, and we're explaining more about it. And of course, plotting, you can plot them. So these patterns are for 7 elements array. It's not for the 19 elements. And it's scanned at 30 degrees. And you can also impose the plot on the architecture or on the structure. That's something that HFSS allows you to do. Okay. So now, let me just go to the final slide I have here and give you a chance to ask questions. So to summarize, phased array simulation, what are the important or essential features that ANSYS offer you, enable design, troubleshooting, prediction of performance of your desired phased array. It offers you 3 options: infinite array option, finite array explicit, and finite array domain decomposition method. We talked about the trade-off between speed, accuracy, and flexibility for each one of them. So you decide based on your need, and those are the consideration will tell you which one to choose. We talked about some important boundaries to be used for the periodic structures, master and slave boundaries. Apply them for different lattice, rectangular and triangular lattice. 2 pairs are needed for rectangular lattice. 3 pairs are needed for the hexagonal cell for triangular lattice. We talked about the Floquet ports and modes. We need them in the infinite array simulation. We take them off in the FDD unit cell, the finite array domain decomposition. Even we take the whole unit cell with its mesh, but we don't take the Floquet ports with us. We replace them by radiation boundaries or perfect match layer or any other absorbing boundary conditions. And we disable any mesh, any additional mesh refinement after importing the mesh from the unit cell to go to the DDM. We talked about how to architect or how to choose, how to kind of like simulate or emulate, simulate the rim of the elements of the aperture you have. You can do whatever rim you want, oval, circular, hexagonal, non-uniform. The way you do this using this create array feature that allows you to choose active and passive elements, embedded elements. Embedded elements are the ones that basically control the rim shape of your array. The passive ones are physical elements, but they are dummy, they are terminated by matched load, and the active ones are the ones connected to your beamforming network. You get the performance through typical indicators we use for all antennas, like return loss, like coupling, patterns, gain, directivity, beam width, efficiency, and side lobe level. Add to this, because we have electronic scanning, so the scan angle impact, and also we saw, or we learned how to set up the scan angle in the infinite array using the master slave boundaries and in the edit source post processing in the FDD, in the DDM, sorry, FADDM. And we also mentioned that the scan angle has an impact on your return loss and isolation and other KPIs. And by that, I conclude my talk. And if any question, we have about 3 more minutes to take any more question needed to be asked. So please. Okay, so it looks like that I haven't received any question. We are open if later any question is needed or is being asked, or any more information needed. Don't hesitate to contact us. And thank you for attending. You have a great rest of your day. Thank you.